When you plug your charger into a wall socket, you are tapping into a lethal supply of high-voltage alternating current. But the processors inside your laptop require a tiny, stable fraction of that energy to operate. If your laptop were directly wired to that outlet, a single component failure could send wall voltage straight into your hands as they rest on the keyboard. To prevent that, engineers use galvanic isolation. It is a method of designing a physical gap inside the power brick. Power has to cross this gap to charge the battery, but the actual electrical current is blocked from making the journey. One of the most effective ways to cross that barrier is a switch-mode power supply, known as the Flyback converter. It uses a very low component count and a trick of physics to pass energy over the void. By disconnecting the grid from the device, the Flyback converter acts as a safety barrier that allows us to interface with high-powered electrical systems without being part of the circuit. The central piece of this circuit is the coupled inductor, widely known as a Flyback transformer. Unlike a standard wire, it is split into two separate coils, a primary side connected to the wall and a secondary side connected to your device, separated by a physical gap. A standard power transformer passes current right through to the other side. A Flyback transformer is designed to store energy in that physical gap as a magnetic field. We control this storage process by adding a switch, typically a MOSFET transistor, to the primary side. When this switch closes, a period called the T-on phase begins. Voltage flows from the wall and charges the primary coil. At the same moment, a diode on the secondary side actively blocks any current from flowing to the device. The energy from the wall has nowhere to go, so it is trapped, expanding into a magnetic field around the primary coil. Capturing the energy magnetically on one side of the gap is the first step. We have successfully pulled power from the grid without allowing the grid's electrical current to cross the barrier. Next comes the discharge, or T-off phase. The primary switch opens. The flow of electricity is cut, causing the stored magnetic field to collapse. As it does, the voltage polarity reverses. This reversal forces the trapped energy to fly back across the physical gap into the secondary coil. The reversed polarity allows the energy to slip past the diode that was blocking it earlier. That burst of transferred energy is harsh, so it dumps into an output capacitor. The capacitor absorbs the spike and smooths it out, delivering a steady DC voltage to your device. To dictate exactly how much voltage reaches the end device, engineers adjust two physical variables: the turns ratio between the coils and the duty cycle, the time the switch is left in the on position. For heavy loads, engineers use continuous conduction mode, where the switch flips back on before the inductor fully discharges. For light loads, discontinuous conduction mode is more efficient, letting the energy drop to zero before the next cycle starts. By timing these phases and tuning the coils, engineers achieve total control over the output voltage across a completely disconnected space. But power demands change constantly. Every time a laptop screen gets brighter, the load shifts. The converter needs a feedback loop to carefully monitor the output and precisely adjust the switching rhythm in real time. One approach is primary side regulation, which estimates what's happening on the output side based solely on electrical data gathered from the primary side. High-precision electronics use secondary side regulation. This measures the output voltage directly and uses an optocoupler to shoot a beam of light across the physical gap, transmitting data back to the primary side without breaking the isolation. Today, this entire dance of timing and feedback has been miniaturized. The control system is now packaged into a single silicon microchip called a Flyback controller. Modern controllers increase efficiency by using synchronous rectifiers to reduce heat. They also integrate thermal failsafes and short-circuit protection, constantly monitoring the primary and secondary current. These chips transform a complex analog concept into a reliable plug-and-play solution that ensures a local electrical fault cannot spread to the rest of the circuit or damage the device's sensitive processors. This architecture scaled up on assembly lines in the 1940s to manage the high voltages required by early television sets. Its isolation capabilities made it mandatory for medical equipment, ensuring that monitoring devices could be connected directly to patients without risking a surge from the grid. When portable computing arrived, this same method provided the lightweight, isolated power conversion necessary to safely step down wall voltage into a battery-powered frame. From early TVs to the charger in your pocket, the Flyback converter is the silent gatekeeper between our electronics and the grid. It is a simple two-step dance of magnetic energy, one that allows us to safely use the power of the wall while remaining completely disconnected from it.